I want to address the question of whether there's more to neural network than a bunch of weight matrices. In other words, are neural networks black boxes that are inaccessible to us, or is there something going on that we can identify? And as you might guess, the answer is yes. So let's sort of very briefly say something about classical AI systems, so symbol-based AI systems. So a key system that we have seen was IBM Watson's Jeopardy player. And in one of the videos, the IBM folks repeated that mantra of IBM Watson: it knows what it knows. And so how does it know what it knows? Well, that information is supported by confidence factors. And those confidence factors were trained by a logistic regression model, which is very similar to neural networks. So again, I mean, they used a boatload of data, and they trained it, a logistic regression model to determine the final confidence values. So I don't know whether the folks at IBM would have been able to explain, where some of the decisions are being made, because they just had so many models. Now, in neural networks, again, we talked about them as a bunch of weight matrices. And what you're going to do looking at these individual weight matrices? Probably not much. So what we need to do is we need to look up, we need to take a broader perspective. So again, neural networks are considered not to have explainability. Be that as it may, we want to look at some processing that is going on in neural networks that process natural language, and particularly want to look at BERT. So BERT was developed by some folks at Google. It stands for bidirectional encoder representation from transformers. I do not want to go into the details. By the way, all the papers that I'm referencing here are hooked up on the daily outline. The idea of BERT, so we have an input. My dog is cute. He likes playing. The key idea is that information, the input, is processed not in sequence. It's processed all at once, in parallel, if you wish. That's different to RNNs, recurrent neural networks, where if they are used for natural language processing tasks, a lot of times they are single direction, from front to back. Some people then sort of said, well, why don't we also go from back to front? And so then they combine these things. But what they did here is they process everything at the same time. So that's the key thing. We don't need to know too much about BERT. But what we need to know about is that that we can inspect and tell a little bit of what it's doing. So for your reference, they had two models of BERT, the base model and the large model. And so the large model is quite big, as you can tell, 24 layers. I mean, remember some of the stuff that we did with MNIST, one layer was just fine, one hidden layer. So it's a huge network, and they trained it on some books and the English Wikipedia. So it came pre-trained. Even the base model is not small, right? 12 layers. So let's see what we can do. So the paper that I want to discuss now and present is by Ian Tenney, Dipanjan Das, and Eli Pavlik. And it's called BERT Rediscovers the Classical NLP Pipeline. And so again, it's linked up over here as well as in the daily outline. So what the authors show, in other words, is that there's structure to the processing of BERT. In particular, BERT seem to have learned that some NLP tasks need to be completed before others, and some lower-level tasks are informed by decisions made further down the pipeline. So what do we mean by the NLP pipeline? So we looked at the Stanford NLP toolkit, at least at the core, and if you remember, we had all these different annotators. We had a tokenizer, we had part of speech identifier, we had a lemmatizer, named entity recognition, and then the parser. And so the idea is we have this pipeline, and some of the things kind of have to happen before other ones. So, kind of need to know the parser of speech is really helpful to know when you do the parsing. So that's the idea. It's a pipeline. So the Stanford NLP toolkit, as we mentioned, even though they use neural networks for some of these individual tasks, everything else is sort of like engineered in the sense that it was developed, software was developed by some people. So how do you inspect a neural network then? What you do is you look at the structure. So you have lots of layers, right? There's lots of stuff to look at. 12 layers, right? Or 24 layers. So let's sort of like look at some of those layers. What they do is they try to figure out what information. Well, let me move on here. They use an approach called edge probing, and so what they do is they sort of like train a classifier in parallel with training the entire network, and then they ask the classifier that they trained the partial classifier, here's an NLP task. What do you think? So what they do is, to be very specific, this is not necessarily a high-level NLP task, but it's sort of like, hey, what is the POS of this word? What is the entity type of this word? All right, so that's what they did with this edge probing. So you can imagine that if we go back to all these layers, they sort of say, well, you know, after 5 layers, what can you reliably tell me about the information that we need to collect about those individual words? So can you tell me after 1 layer or after 2 layers or after 3 layers, you know, what the POS is or what the name or what the entity type is? That's what they're asking. That's what we mean by edge probing. And so presumably, if you can tell reliably what the part of speech is at a fairly low layer, like after maybe 3 or 4 or 5 layers, then we kind of know that, that decision is made. But for example, if you need to do named entity recognition and you really can't tell, you know, after a few layers, you know, the information is not very accurate, then again, maybe after 7 or 8 or 9 or 24 layers, you can tell. So that's the idea. And we sort of like have all these partial networks that were trained, and then we sort of like asking questions. And again, it's very important that we sort of have some sort of accuracy metric, and that's typically what's called the F1 score, which is a combination of the precision and recall. So that's the idea. So let's see. Here are some things that they were interested in: parts of speech, dependencies, co-reference, semantic proto-roles, relation classification, semantic role labeling, all those things. So they looked at all those things based on 1 layer, 2 layers, 3 layers, 4 layers, 5 layers, and so on and so forth. All right. So here's what they found, and we'll show that here in a moment, that POS tags were processed earliest. Then BERT looked at constituents, or determined, had reliable information about constituents, then about dependencies, then about semantic roles, and then about co-reference. Okay, so the idea is some of this stuff is basic syntactic information. It appears early in the network, while high-level semantic information appears later in the network at the higher levels. So I don't want to go into the technical details of how they determined it. Rather, I want to show you the results that they were able to determine. So what they have over here is, again, we have many layers, 24 layers, so that's large. And we're going to look at the blue data. And so what they determined is, and this appears to be acceptable practice, is that how high are the weights at a certain layer, okay? And so what they determined over here is that POS, the POS tagging weights seem to be very high over here. So what do we have? Around 12 layers. So notice this decision is not necessarily made very early on. And then constituencies are a little bit later, dependency a little bit later, entities a little bit later. Notice that they sort of like fairly broad throughout this thing. Semantic role labeling, again, a little bit later. Co-reference resolution a little bit later. And then this one here is sort of like fairly strong throughout the layers. And we say a few things about this here in a moment. So the idea, though, is you can sort of like tell that you know, these decisions are kind of like made over here. These are over here, and so on. So it goes just a little bit to the right. They interpret the higher weights as evidence that the corresponding layer contains more information related to the particular task. Okay, so that's kind of like the big idea. So syntactic information they found is more localizable, and so we can sort of like do that over just a few layers. Semantic tasks are spread across the network. So notice that the SPR task is close to uniform. So they were able to resolve non-trivial, trivial tasks very early on, but non-trivial tasks requires almost all the layers. Okay, so let's have a look at that one. It's just you just can't do that in one or two layers. It just requires information from all the layers. Again, for many tasks, they found that the differential scores are highest in the first few layers. So layers 1 to 7 for BERT, i.e. most examples can be correctly classified very early on. So that's kind of really interesting. So they attribute that as an availability of heuristic shortcuts. So again, challenging examples may not be resolved until much later. Many cases can be the easy ones can be guessed from shallow statistics. So that's kind of interesting, right? Perhaps that's why Google Mail is sort of like able to sort of like respond with canned emails very easily. All right, so let's move on. Again, we already talked about this a little bit. Semantic relations SPR task, they show continued improvement up to the highest layers. We'll see some examples here in a minute. Some of the stuff is really hard. Whether something is an organization or a geopolitical entity. So the example that we're going to look at here in a moment is Toronto. And so some of the stuff we just can't resolve at early layers. It just takes a little bit more time. So let's have a look at two examples from the paper. So here is a phrase that was posed that they investigate. He smoked Toronto in the playoffs with 6 hits, 7 walks, and 8 stolen bases. So everybody kind of immediately knows, they're talking about baseball, right? Hits, walks, stolen bases, playoffs. And so the question then is, what do we mean by Toronto? Is it a geopolitical entity, like the city? Or is it the Toronto Maple Leafs, I believe, the baseball team? So let's see what happened. So originally it assumes that, or the processing suggests that the network thinks that, oh, it's a geopolitical entity. So notice that this is BERT base, it only has 12 layers. So they indicate GPE. So notice that initially Toronto is a GPE, geopolitical entity, and then eventually they realize, oh, wait a minute, it's an org. Okay, so that's all like what they realized. And they also talk a little bit about semantic role labeling. That sort of really helps out. What do they mean by Toronto? So smoked arg1. What is the type of arg1? And so again over here, arg1, they sort of realize that, oh yeah, it's an org. Again, it sort of started out as something else. Another example is China Today blacked out a CNN interview that was. So the question is, what does today refer to? So originally, they assumed that today was, well, as in what is today, November 10th. And so they assumed it was a noun phrase. But eventually, they realized that, oh, actually, there's a TV show called, or a TV channel called China Today. So it's a proper noun. And so eventually, that sort of like came up over here. So the proper noun got to be higher. And so again, that was done based on some context that they had. So there you have it. So they have shown, or at least contributed to the body of evidence, that there is some structure going on. It reminds me a little bit about what CNNs do. We talked about that a little bit, that very early on they sort of look at some fairly low-level patterns like lines, for say edge detection, and then eventually they were able to compose images of faces and so interpret them properly. And so, we apparently have something very, very similar here when we talk about neural networks that process language. All right, so very briefly, The paper has shown that deep language models can represent the types of syntactic and semantic abstractions traditionally believed necessary for natural language processing, and they can model complex interactions between different levels of hierarchical information. So that's pretty impressive. Alrighty, folks, I'll talk to you later. Bye.